Hello again, this is Turgay Gorkar, and this session is about the details of two-dimensional erasure-coded LTO with rail architecture. There are two subsections. First, I'll be discussing the real-world tape errors and how do you calculate durability for cold storage models, and then subsequently go in details on the erasure-coded tapes and rail architecture. The key here is this locally repairable two-dimensional erasure-coded tapes. The local repairability is one of the key features. It's a quantum's patent-pending two-dimensional erasure code technology, offers the ability to read erasure-coded files or objects using single tape, however, with the protection of multiple tapes. Typically, erasure code and tapes are not like disk drives and erasure coding object stores, because in this world, hard disk world, you get all the disks are up and running and available 24/7. So when you erasure code and distribute your file object, let's say 100 megabytes across multiple disks, you can access them, any one of them, automatically right away there, or they're available. If one is not available, the system can detect it, repair it, move data around in the background to keep the durability active. But with erasure-coded tapes, when you take the same, let's say 100 megabyte file, do the similar thing as you typically do in the disk drive, spread it over multiple tapes. Now you need multiple drives to access that file. That results what we typically describe as long tail latency problem. This technology, this two-dimensional erasure code technology, solves this issue. It has, as we discussed, is two dimensions. They're orthogonal to each other. One is called per tape, the other is multi-tape. Per tape erasure typically provides 11 nines durability for most real-world tape errors beyond tape format user bit error rate errors. However, when you start using two-dimensional feature, now you also cover the other types of errors that typically you need a second tape to solve, such as the tape is damaged, pin dropped, tape cut, tape shredded, those type of rare events, but nevertheless, they're things that you need to consider and plan for. So the combined together, you get 15 nines of durability. Now you would say, well, yes, but what about the overhead? Well, interesting enough, the overhead for this technology is less than a 2-copy overhead. So in a 2-copy overhead, you got 100%. 3-copy overhead, you have 200%. With this technology, you have, based on your policy selection, you'll have less than 60% overhead, but with much higher durability numbers. Repairs are done locally. So to repair a tape, if you have a bad section, edge damage, or things in that nature, where the rest of the tape is still good, you can repair that entire content without needing another tape, without ever needing the copy tape or other erasure-coded tapes. So that's a key feature, is locally repairable two-dimensional erasure code. Certain types of severe errors where you have too many random errors or too many drive-related issues, you can use what we call iterative decoding. And I'll go over this thing. This is row column type decoding concept. And it also is ideal when you're reading files with tape drives, which typically tape drives go through various recovery routines with packages, underruns. In this technology, you can disable that feature and read everything on the fly. Why? Because you got the per tape dimension to help you with. It works with Rail, which is redundant array of independent libraries. What we mean is with multiple tapes, erasure coded, individual tapes have individual per tape erasure code. It's ideal with Rail configuration where you use multiple different libraries, individual robots, which works in an aggregate fashion to provide you with the best availability and also supports this two-dimensional erasure code in an idealistic manner. Tape errors and dimension, two-dimensional EC. Which one deals with which types of errors? First of all, it's in the blue chart section. The green chart talks about benefits of the tape. We covered that thing previously. We all know about the benefits. But here is in the errors corrected by per tape EC. Nearly almost all your media drive related issues, can be taken care of by this per tape EC. You can disable the retries and just skip over that error region and continue reading your data. Let per tape EC at the host level correct for it. Media stagger wraps, tracking, BOT, EOT, or directional errors, correlated errors. Local errors due to media wear, edge damage. These can be taken care of just simply by per tape EC. What per tape EC cannot take care is human errors, lost, stolen tapes, tape cut, tape shred, pin drops, those type of errors. For those, you need the multi-tape. So together, multi-tape with per tape will provide you with two-dimensional erasure code where you can, enjoy more than 15 nines durability with efficiency overheads less than 60%. Types of errors, a deeper dive into types of errors, and basically what we have here is a chart that is based on Quantum's years of experience with LTO technology. The first row is what we discussed earlier, that is the bit error rate. It's 10 to the 19 and 11 nines durability. But when the errors are beyond the capability of internal C1, C2, then you get into other rows. Things such as defects, new acceleration of post-write scratches or defects, edge quality problems, bad CM, local worn sections due to start-stop back hitches. These are typically less than 0.05%, which equates to 4 nines, and both per tape and two-dimensional EC can take care of it. Lost, damage, misplace of human factor, about 1% based on our experience, and less than that. Basically, you get 2 nines or less. And so it's a substantial issue. Somebody needs to take care of it. That's why you need your copy. In this case, multi-tape EC. Pin drops, tape stiction, tape cut, tension control type issues that causing permanent scratches, less than 0.001%, which is about 5 nines. And yes, two-dimensional EC takes care of this issue with one per tape EC in an iterative manner also. Typical correlated drive and tape errors, read errors, and these are common things which drive uses internal retries, or you move the cartridge from one drive to another drive. Now you don't need to do that. You basically use per tape EC to take care of it. In some severe cases, you use two-dimensional EC. Quantum's durability and availability model for nines estimation. What you're seeing here is a system description, which says, you got N tapes using N comma K multi-tape erasure code policy, and each tape has N1 comma K1 local erasure code policy. Both are orthogonal to each other, and together they form the two-dimensional erasure code. The model is based on Quantum's own internal developed MATLAB Python-based simulation system. And we use a modified Markov model. Now, why we do this? The reason for that is cold storage is different than hard disk drive based 24/7 available systems where erasure codes are used. Chart is number one here. This plot here talks about typical Markov model that shows for disk-based object stores where you get two states, either available or fail. This example shows for 3 copies. So you start with 3 available. Then when you lose one of your drives, you got 2 available, 1 fail. You're trying to repair. While you're trying to repair, you lose another one. You get 1 available, 2 fail, and you're trying to repair this thing. And while you're repairing it, boom, you get a 3rd failure. Now you lost your data. So by the repair rates, making sure you can repair fast enough, you can always recover the data. That is disk-based system, but tape is not like that. You can use this model for tape by certain assumptions, but if you want to get a detail with these type of nines calculations, then what we found out is best to use a modified model called, non-homogeneous CT Markov process with an additional state, an additional state being the detected state. The reason behind that is tapes are stored with data at their silos in the library, assuming tapes stay with library in this example. And you don't know, system doesn't know if there's a failure in the tape until the tape is loaded. So once the tape is loaded in the drive, now you can detect if the tape is a failure or not. So by using this additional state, we basically add 3 more states to this simple example. Whereas when you use different policies, 2-dimensional erasure code, copies, with rail architecture, this picture here that you see gets to be complicated. So it's difficult to solve it with a closed form equation like you typically do with the disk-based systems. So we end up using this developed model to calculate the mean time to data loss, mean time to data unavailability numbers. And from this study, we can basically predict what type of nuns you're going to get for a configuration that you design. This one is basically a summary of what we discussed. You get 2 copies, and in this column, you got 2-dimensional erasure code. Key differences is you got 100% overhead versus 45% overhead, 10 nines versus more than 15 nines. And that basically is because it's the feature of 2-dimensional EC and with this repair characteristics and this modeling-based study. How do you do this thing? What's the basic concept behind that? Basically, each file or object gets erasure coded with local parity and written to an individual tape. You don't stripe files, objects, erasure code across them. Then once you write them individual tapes with their individual local parities, you then calculate the parity tapes. And then once you calculate the parity tapes from the data tapes, then you have your system. A simple example of how do you calculate parity tapes? Well, when you do that, you also need to consider correlated errors. Example, what is a correlated error? Well, correlated error is, for instance, in a tape system, you pick all the chunks and the beginning of each tape to generate your parity chunks. Well, if you have a BOT type tracking problems, they're going to be affecting all your erasure code data chunks, symbol chunks. So now you run into correlated errors with your erasure code is not powerful enough. This one does differently because we can pick up any chunks to generate parity chunks. So here we basically rotate it to pick up the chunk such that they're not all aligned at BOT. If you have a BOT problem tracking example, hypothetically, you would lose only one chunk in this example. So that means your errors are randomized. And the randomization with the use of two-dimensional erasure code with orthogonal ECC and iterative decoding is what really gives this 15 nines or more durability. Example of an iteration. Now, this is a simple example to make this thing fit on a page. Multi-tape 7-2, 2 parities, per tape 5-2, 2 parities. So anything more than 2 X's in a tape, you cannot decode. Well, in here, I want to restore file A from tape number 1 here. Well, it's too many errors, but the tape is still good. So what I do is I decode rows 1 and 5, and I correct those things with the other tapes, and now I have remaining errors. In these remaining errors, I still can't get file A. Okay, what I do is then I go column decoding. I decode columns 2, 4, 5, 6, and 7. That leaves me columns 1 and 3. Unfortunately, it's still not solved. I cannot get my file A, but however, I can now do row decoding. Row decodes 2, 3, and 4. Each one of these rows are 2 parities, and I correct all the errors. Now, I started here doing row, column, row decoding. I corrected all the errors with all the tapes. Now, not only I restored my file A, but I can also repair my failed or damaged or suspect tapes. Here's an example. It's an actual demo. We've taken 2 different tapes, did 2 different damages to the tapes. You cannot read this data with a standard software. It just will fail. Drive will do 20 minutes of retries and just basically give up after 20 minutes. So trash in its head, magnetic head. So it's not good for media. It's not good for tape drive. In this case, media was bad anyway. However, we can restore the data if you use the per tape erasure code software algorithm. What it does is it just skips over these regions and uses its internal parity to correct for it. So you don't need to go get a copy. You don't need to go get other erasure coded tapes. Don't need to find out how else I can record it, or I'm only going to get data before and after this thing. None of that thing. You can get your original file with 11 nines durability. And this slide finally talks about the redundant array of independent libraries, Rail. And since we have erasure coding, since each file is its own tape and they're all erasure coded, protected with parity tapes, ideal situation is put them all in individual libraries. When I do that, I get one big aggregated library with massive number of robots. Each one of them is helping me working. If one fails, I can get data from all the other. They're independent, but their software connects them together. So overall, I get a better performance, better available system. Also, I got a higher performance due to the small file restore capability, or restoring. I have a data set. I want to restore 1% of my data set by touching all my cartridges. You know, if it's requirement like that, we can do this better with this architecture compared to enterprise. So overall, it's a yes, we have developed a new erasure coded concept, 2-dimensional erasure code. It solves the latency problems. It addresses the durability, performance, and TCO concerns. Thank you very much. This is Turgai Gokar.